Hey everyone. In this video, we're going to talk about how to solve linear inequalities. Solving a linear inequality is actually the same exact process as solving a linear equation, where we want to go through and isolate the variable. However, there's one extra important rule for solving inequalities that we have to keep in mind. And that rule is when you are multiplying or dividing by a negative number, we need to reverse the inequality symbol. So this is a rule that we have to use, but first I want to explain why we have to do this. So let's just think about a simple example, and we'll think about it on the number line. So why don't we consider the inequality, let's say 1 is less than 2, which we know to be true. So on the number line, so 0, 1, and 2. So because 1 is to the left of 2, it's less than 2, okay? But now let's multiply both sides of this inequality by negative 1. So I'm going to multiply by negative 1 on both sides, and now let's see what happens. So now what I end up with is I have negative 1, and then I end up with negative 2. Well, if I look at those on my number line, so here's negative 1, and here's negative 2. If I look at their location, now negative 2 is to the left of negative 1. So that means that in this inequality, negative 1 is actually bigger than negative 2. So whenever we're dealing with inequalities, when we multiply or divide by a negative number, we're actually switching which one is bigger and which one is smaller. Another way you could think about that is because 2 is farther away from 0, when we multiply by negative 1, negative 2 will also be farther away, which making it a smaller number. So whenever you multiply or divide by negative, we need to switch the sign so that our inequality still makes sense. Okay, so keeping that in mind, let's do a couple examples. So the first one, negative 3x minus 5 is greater than negative 26. So like I said, the process for solving these is exactly the same as solving an equation. So we want to start by isolating our variable term. So let's start by adding 5 to both sides. So that's going to give me negative 3x is greater than negative 21. All right, and to isolate my variable, we're going to divide by negative 3. And here's where that rule comes into play. So because I'm dividing by a negative value, I need to switch this sign. So I end up with x is less than 7. Okay, I have a couple different ways I can represent this solution set as well. The first one is with this inequality. I could also use set builder notation. Set builder notation, we use fancy brackets, and then I'm going to say x, and then we do a straight line. The straight line represents such that. So basically what I'm saying here is I have a set of values. I have the set of x values such that x is less than 7. So it's describing all these numbers that are less than 7. So this is set builder notation. Another way I could describe this is using interval notation. In interval notation, we're describing a range of numbers that fit our solution. So in this case, we want all of the x values that happen to be smaller than 7. So what we start off with is, well, all the ones that are smaller than 7, that can go all the way to negative infinity. So that's where I'm starting. And then I can go all the way up to 7, and then we're going to stop. So I'm using a parentheses here because we're not actually including 7. If this was less than or equal to, then I would use a square bracket. But this is interval notation. And the last way we can represent this solution set is on a number line. So let's put a line, and then on this, I do need to put my interval. So I have this value of 7 where x is less than that. So I just need to make sure that's on my number line somewhere. And then to indicate the scale, so if someone else is going to look at my graph, they know exactly what they're looking at. I'm going to put a couple more numbers. So we'll do 1 or 2 on the right-hand side of 7, and then we'll put a couple more on the left-hand side, just to give everyone an idea of the location and the scale of this number line. All right, now we want x is less than 7. So at 7, because we're not including 7, we don't have the or equal to part, we're going to use an open circle. All right, that indicates we're getting right up next to 7, but not quite there. And then to represent this entire inequality, we're going to shade the part of the number line that represents our solution set. So we want all the values that are smaller than 7. So we want everything that is less than 7. So you can shade this. I like to do a little squiggly line to indicate it. And then I'm just going to show that this does go on forever all the way to negative infinity. So 3 different ways we can represent this solution set. Let's try one more example. This one's a little bit more complicated, and it involves some fractions. But we do have ways that we can work with inequalities like this that make it relatively straightforward. So the first thing I want to do is I actually want to get rid of all these fractions in one simple step. And to do that, I'm going to multiply both sides of this inequality by the common denominator of all of these fractions. So I have 3, 4, 6, and 2. So the smallest number that is divisible by all of those is going to be 12. So let's multiply both sides of this inequality by 12. All right, now when we do this, each term is going to get multiplied by 12. 1/3 times 2x minus 4, that's all one term. So the 12 gets multiplied by the 1/3. And then I'm going to distribute the 12 to 3 over 4. So I'm going to write it like this, 12 times 3 over 4. And that's greater than. And then distributing 12 to both terms on the right-hand side, we get 12x over 6, and then minus 12 over 2. So each of the numerators got multiplied by 12. The reason we picked out this common denominator is now all of these fractions are going to simplify. 12 over 3 simplifies to 4. Here, 12 times 3 divided by 4. I could do 12 divided by 4 is 3, and then 3 times 3 is 9. Or you could look at it as 12 times 3 is 36, divided by 4, you also get 9. So then this is greater than. Here we have 12 divided by 6 is going to be 2x, and then 12 over 2 is 6. So in one nice step, we were able to simplify all these fractions, and now we're left with a straightforward inequality. So let's finish this up. The first thing, I'm going to distribute the 4. 4 times 2x is 8x. 4 times negative 4 is negative 16. And then on the other side, 2x minus 6. Okay, negative 16 plus 9, that's going to be negative 7, greater than 2x minus 6. Let's group up our variable terms. Now I can move them either direction, but just thinking ahead, I like to end up with my x values on the left-hand side of the inequality, just out of habit, and it's easier to read them that way. So because of that, I'm going to subtract 2x. So that way my x values are on the left-hand side. And then let's add 7. So now we end up with 6x is less than 1. And then to finish up, we'll divide both sides by 6. So we end up with x is greater than 1/6. Okay, so again, just to run through our 3 different representations for this, we can use set builder notation. So all the x values such that x is greater than 1/6. I can use interval notation. In this case, I'm going to start at 1/6. Again, I'm using a parenthesis here because we're not actually including 1/6. And then it's everything bigger than that. So from 1/6 all the way to positive infinity. And then the last way on a number line. And again, we need to indicate our interval. And I'm going to space this out a little bit. And when I'm doing the interval, I am going to put whole numbers. And then what I'm going to do is I'm going to put somewhere around 1/6. So this is a half. This is about a third. So at 1/6, I'll put my open circle. And then I'm actually going to label that, just so people don't have to guess as to where it is. I can label it and they know exactly that's at the point 1/6. And then we want everything that is greater than this. So we're going to shade everything to the right of 1/6. And again, I'm putting a little arrow on here to indicate that it is going all the way to positive infinity.